What specific problem does the new method or algorithm aim to solve?
The new method or algorithm, introduced in the paper, aims to solve the problem of the inherent linearity of intermediate embedding transformations within transformer decoders. The study focuses on analyzing the linearity properties of transformers, specifically decoders, during pre-training and fine-tuning phases. The goal is to address the challenge posed by the almost linear properties of the embedding transformations between sequential layers in transformer decoders. By introducing new algorithms for depth pruning of transformer decoders, a novel distillation technique involving pruning and replacing certain layers with linear approximations, and a new regularization approach based on cosine similarity, the method aims to optimize model efficiency and effectiveness. The ultimate objective is to pave the way for more computationally efficient transformer architectures without sacrificing their performance, thereby tackling a critical challenge in deploying these models.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method or algorithm works by first analyzing the linearity properties of transformer decoders, specifically focusing on the embedding transformations between sequential layers. The study quantifies the linearity using Procrusta's similarity analysis, which measures the degree of linear dependence between sets of embeddings. The linearity score is calculated by normalizing the matrices of embeddings and finding the optimal linear transformation that minimizes the squared errors. This approach provides a robust evaluation of the linearity of embeddings, considering the scale variance across transformer layers. The analysis reveals a high degree of linearity in the embedding transformations of all tested transformer decoders, with scores close to 1, indicating almost perfect linearity. The method also explores the dynamics of linearity during pre-training and fine-tuning stages, showing a gradual decrease in linearity during pre-training and an increase during fine-tuning. Additionally, the algorithm involves introducing specific regularization terms during pre-training, such as MSE and cosine similarity, to adjust the relations between embeddings within transformer layers. The cosine-based regularization term encourages embeddings from sequential layers to align closer to each other, effectively reducing their angular difference. This method enhances model performance by promoting consistency across layers. Furthermore, the algorithm exploits the inherent linearity of transformer layers for pruning, sequentially removing the most linear layers, replacing them with linear approximations, and incorporating distillation loss to minimize performance degradation. The training focuses on fine-tuning the linear replacements to mimic the original layer's function, resulting in a reduction in model size without significant performance loss.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the method described in the paper include the ability to optimize transformer architectures by leveraging the inherent linearity of transformer layers for efficient pruning. By sequentially removing the most linear layers and replacing them with linear approximations, the model size can be reduced without significantly compromising performance. This approach not only improves computational efficiency, but also maintains high model performance on benchmark datasets. Additionally, incorporating a distillation loss during training helps minimize performance degradation, ensuring that the linear replacements effectively mimic the original layer's function. Overall, this method offers a lightweight and effective way to enhance model optimization, improve efficiency, and preserve model effectiveness, addressing critical challenges in deploying transformer models.
How is the method validated or tested?
The method is validated or tested through pre-training experiments using the Mistral architecture with model sizes of 150M and 650M on carefully selected clean datasets, tiny stories, and tiny textbooks. Specific loss terms are introduced to adjust the relations between embeddings within transformer layers, including MSE regularization term, and cosine similarity regularization term. The most promising results are achieved using a cosine-based approach that encourages the embeddings of sequential layers to converge, effectively making the cosine similarity between them closer to 1 on average. The effectiveness of this approach is evaluated through validation using GPT-4 on tiny stories prompts, linear probing techniques, and evaluation on superglue benchmarks. The results show that embeddings from the model pre-trained with regularization exhibit better performance compared to those from the standard model. Additionally, linear probing on outputs of all the layers of the Mistral 650M model, both pre-trained with and without cosine regularization, on the X-story close-end task from superglue, further confirms the effectiveness of the method. The results indicate that embeddings become more similar across layers with regularization, prompting the model to compensate by amplifying nonlinear processing capabilities in the residual stream. This validation process provides insights into the adaptive mechanisms of transformer models in response to altered internal dynamics.
What results were achieved with this new method?
The new method introduced in the paper achieved significant results in improving the linearity of transformer models through regularization during pre-training. Specifically, the cosine similarity regularization term was found to be the most promising, encouraging embeddings from sequential layers to align closer to each other, resulting in a higher cosine similarity between them. This method led to enhanced model performance, as evidenced by lower linearity scores at each layer of the model after pre-training with such regularization. Additionally, when evaluating the expressiveness of embeddings through linear probing tasks, the model pre-trained with cosine regularization exhibited better performance compared to the standard model. This outcome indicated that the regularization approach not only improved the linearity of embeddings, but also potentially enhanced the model's nonlinear processing capabilities in the residual stream. The results demonstrated the effectiveness of leveraging linearity properties for model optimization and efficiency, showcasing the potential of the new method in enhancing transformer architectures without sacrificing effectiveness.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method described in the paper include the potential reduction in variability as embeddings become more similar across layers due to the cosine-based regularization, which may lead to the model compensating by amplifying nonlinear processing capabilities in the residual stream. This phenomenon could impact the model's ability to capture diverse and complex features, potentially limiting its overall expressiveness and adaptability. Additionally, the approach of sequentially removing the most linear layers for pruning may result in a loss of nuanced information encoded in those layers, affecting the model's performance on tasks that require a deep understanding of the data. Furthermore, the replacement of pruned layers with linear approximations and the incorporation of distillation loss may introduce additional complexity and computational overhead to the training process, potentially making it more resource-intensive and time-consuming. Finally, the effectiveness of the method may vary depending on the specific architecture of the transformer model and the nature of the tasks it is applied to, highlighting the need for careful consideration and evaluation before implementing such pruning techniques.